This lecture is over the time value of money. I'm your professor, Dr. Stephen Haggard. The basic idea of the time value of money is that a dollar today is worth more than a dollar tomorrow. Why is a dollar today worth more than a dollar tomorrow? Well, I call them the 4 I's. The first I is inflation. Inflation is the tendency of prices to go up over time. When my grandfather was a boy back in the 1920s, he could buy a candy bar for a nickel. Can you buy a candy bar for a nickel today? Absolutely not. If he had just held on to a nickel instead of buying a candy bar, he wouldn't be able to buy a candy bar with that nickel today. He'd have to have several more nickels to buy the same candy bar. And so the nickel in 1926 was worth a lot more than a nickel is today. The second I is interest. If someone gave me the choice between getting a dollar today or a dollar a year from now, I would say give me the dollar today, and I could put it in the bank and earn interest, and at the end of the year I would have something more than a dollar, as opposed to the single dollar that they would be offering to give me at the end of the year. The third I is investment. I could take the dollar today and invest it in stock. Now I might not be earning interest, but at the end of the year, the value of that stock might have gone up to something more than a dollar, and I could sell it and make money. And the fourth I is impatience. Humans are impatient animals. We would all rather have something now rather than later. Even if there were no such thing as inflation, interest, or the ability to invest our money, we would still rather have a dollar today than a dollar a year from now. Everything in finance happens on a timeline. To the left, we have the past, and to the right, we have the future. Now, there's some confusing nomenclature in finance: present value and future value. If I told you that I have an account that has $1,000 in it today, would that be the present value or the future value? Well, it would depend on the problem. If I told you I had invested that money today in hopes of having a larger amount of money in the future, then the $1,000 would be the present value. However, if I told you that my grandmother invested $32 in an account in the 1930s that was worth $1,000 today, that $1,000 would be the future value. In truth, all present value means is coming before future value, and all future value means is coming after present value. Don't be confused about the timing of a cash flow. You could have a cash flow that happens in the future that's actually the present value. For instance, I plan to start investing money 10 years from now. I will put a lump sum of money in an account, and I will withdraw it 20 years from now. The amount that I put in 10 years from now would be the present value, even though that cash flow is taking place in the future. We have a formula that allows us to find the future value given the present value, and we can also change it around so we can find the present value given the future value. Now we're talking about single cash flows here, or lump sums, not a series of cash flows. And here's the formula. Future value equal present value multiplied by open parentheses 1 plus r close parentheses to the t power. Now, for those of you who have forgotten algebra, the way we would do this is to start with what is inside the parentheses, the 1 plus r. That r is the required rate of return, or the discount rate. If it were 10%, then inside the parentheses we would have 1.10. Now, the t is the number of periods over which we are discounting. If our interest rate was on an annual basis, then t would be in years. If our interest rate were on a monthly basis, then t would be in months. If we have an annual interest rate and we are looking over a 3-year period, then we would simply take 1 plus r to the third power. Once we find that, then we would multiply by the present value to find the future value. Here is the rearranged formula to allow you to find present value given a future value. All we have done from an algebraic standpoint is to divide both sides by 1 plus r to the t. Recall that in algebra, as long as we do the same thing to both sides, we're perfectly fine. When we divide both sides by 1 plus r to the t, on the present value, the 1 plus r to the t cancels out. Now we'll look at the single period case. For the single period, the t becomes 1, so the formula is merely future value equal present value multiplied by 1 plus r. If I invest $1 today, what will it be worth 1 year from today if the rate of return is 5%? Well, we just plug everything into the equation. The dollar today is the present value. R is 0.05, that's the decimal equivalent of 5%. And when we do the math, we come out with 1.05. We can also find the present value of a future value in the single period case. Once again, t is equal to 1 for the single period, so present value is equal to future value divided by 1 plus r. This process is called discounting because the present value is going to be less than the future value. So if you hear the term discounted cash flow analysis, we're merely talking about finding the present value of future cash flows. So let's start out and say that we have $1.10 in our account today. We earn 10% on the investment. How much did you deposit 1 year ago today? Now this is a prime example about how people can get confused between present value and future value. Even though that $1.10 is today, it's not the present value, it's the future value. That amount that we deposited 1 year ago today is the present value. And so we plug into our equation the future value, $1.10, divided by 1 plus 0.10, we find that the present value is $1. Now we're going to introduce another very important concept from finance. It's called net present value, and it represents the increase in a person's or corporation's wealth as a result of taking on a project or an investment. Mathematically, net present value is the present value of the future cash flows from an investment minus the present value of the cost of the investment. Here's an example. You can pay $95 today for an investment that pays you $110 1 year from now. Your required rate of return is 10%. What is the NPV or net present value of this investment? Here we are continuing with our NPV example. Once again, you can pay $95 today for an investment that pays $110 1 year from now. Required rate of return is 10%. What is the NPV of this investment? Well, the present value of those future cash flows is merely 110 divided by 1 plus r, which is 1 plus 0.10 in this case. That is $100. The present value of the investment cost is just $95. Why? That investment is happening at time 0 of this problem. What is $1 today worth? $1. What is $95 today worth? $95. In fact, if you wanted to put this through the formula, you could. T would simply be equal to 0. What is anything to the 0 power? 1. So we'd merely have 95 divided by 1. Now we can find the NPV. The NPV is merely the present value of the future cash flows, 100, minus the present value of that investment cost, $95. That gives us an NPV of $5. Now, a positive NPV is a good thing. Recall that we said that NPV represents the increase in wealth as a result of making an investment. We like positive increases in wealth. We don't like negative increases in wealth. Since NPV is positive here, this is a good investment. Now we're going to move on to the multi-period case. Now when we get into the multi-period case, we start to see something called compounding, which is the earning of interest on interest. If you invest $1 today at 5% interest compounded annually, how much will you receive if you withdraw your investment 2 years from now? Well, we know that it's present value times 1 plus r to the t power. T here is 2. And so basically what we're doing is taking that initial dollar and multiplying it by 1.05 and multiplying it again by 1.05. If you put that through your calculator, you'll see that it's 1.1025. That extra 0.0025 is as a result of compounding. Now, why do I say it's extra? If we were doing simple interest, where we only earned interest on the principal or the initial dollar we invested, at the end of 2 years we would only have $1.10. We would have 5 cents from year 1 and 5 cents from year 2. Where did that extra 0.0025 come from? Compounding, the earning of interest on interest. That nickel that we earned in year 1, the interest on it in year 2 was 0.0025 cents. Let's talk about the difference between simple and compound interest. Simple interest is only earned on the principal or the initial amount invested. Compound interest is earned on both the principal and any interest previously earned. But watch out, if you withdraw that interest, you won't be earning further interest on it. So we have to throw the caution in when we are discussing compound interest that the interest is not withdrawn after it is earned. Okay, recall from our basic time value of money equation that future value is equal to present value times 1 plus r to the t power. Now we can apply this to our last example, where we have the future value being equal to $1 multiplied by parentheses 1 plus 0.05, which is our 5%, close parentheses, to the second power, because we're dealing with 2 periods. And when you do that math, you get 1.1025, so a little more than $1 and a dime. We can also use our financial calculator to solve this problem. Here's the TI-BAII Plus, and the first thing we want to do is hit second and future value. That clears the time value of money. I'm going to put 1, present value, 5, I per Y, 2, N, that's the number of periods, and then I'm going to compute the future value. Now notice that the number is the same, 1.1025. However, there's a negative sign next to it. Why is this? That's the sign convention for the TI-BAII Plus. Present value and future value are cash flows in opposite directions. For example, if I put money into the bank today, that's money out of my pocket. And when I withdraw that 2 years from now, that's money in the other direction, flowing back into my pocket. And so that's why we see the sign convention being this way on the TI-BAII Plus. Now, does it matter which is negative and which is positive? Absolutely not. We could have put present value in as -1, and we would have received 1.1025 positive back as our answer. Let's talk about present value and discounting. Cash flows from the future are not worth as much as cash flows today. Therefore, we must discount future cash flows to find out what they're really worth today. The present value represents what we would be willing to pay today to receive the future value in the future. We are indifferent between receiving the present value amount today or the future value amount in the future. Indifferent means we don't favor one over the other. They are both equally attractive to us. Let's work another example. You are offered an investment today that pays $121 2 years from today. Your required rate of return for this investment is 10%. What is this investment worth to you today? What they're asking for here is a present value given a future value, a rate of return, and a number of periods. Now we could use our time value of money equation on this and it would work just fine. Present value equal future value divide by 1 plus r to the t. In this case, future value is 121, and 1 plus r is 1 plus 0.10, that's our 10%, the 0.10, to the second power, that's our 2 years. And if we do that math, we get $100. But we could also work this out on our TI-BAII Plus. First thing we want to do is clear out our calculator's time value of money keys. So we hit second and future value, that says clear TVM. I'm going to put in 121 for the future value, 10 for I per Y, that's the interest rate, 2 for N, that's the number of periods I'm going to compute present value. Notice that we get 100. Now it has a negative in front of it, but remember that's simply because of the sign convention for the TI-BAII Plus calculator. So far we have found future value given present value and present value given future value. That's pretty easy stuff. But what if I ask you to find the interest rate? Well, we can simply rearrange our time value of money equation. Here I show the steps to do that. We'll start with the future value expression of the time value of money equation, and then we'll divide both sides by present value. Now we need to get rid of that t exponent. How do we do that? Take both sides to the 1 over t power. So the exponent on the right hand side, t times 1 over t, will cancel out, and we are left with future value over present value to the 1 over t power is equal to 1 plus r. Now to get r by itself, we merely subtract 1 from both sides. Let's work an example now on finding the interest rate. An investment of $100 provides a single payment of $133.10 3 years from now. What is the interest rate? Now notice I have annual in parentheses. Remember that unless you are told otherwise, we are to assume that interest rates are on an annual basis. Earlier we solved for r in our time value money equation, and we found that it's future value over present value to the 1 over t power, and then subtract 1 from the whole thing. When we do that, we can find that the interest rate here is 10%. Now that kind of calculation on a calculator tends to be troublesome for students, so we can also accomplish this on our TI-BAII Plus. First of all, we're going to do second, clear TVM. I'm going to enter 133.10 for future value, 100 and the plus or minus key to make it negative, present value, 3 for the number of periods, or n, and then I'm going to compute I per y. We get exactly the same interest rate this way as we did through using the time value of money equation. Now notice that I put in present value as negative. Why must one of those or the other be negative? Because otherwise we would have an error. Remember the sign convention on the TI-BAII Plus. Those are cash flows in opposite directions. But what if we're forgetful and we don't do that correctly? Well, I can replace that negative 100 in present value with a positive 100, and we'll try computing I per y again. The calculator returns something called error 5. However, it might be helpful for you to think of this as being error S, and the S stands for signs. It means you've got a problem with your signs and you should go back and fix it. How could I fix it? Change the sign on either future value or present value. Just to demonstrate, I'm going to change it on future value. 133, oh, I got to hit clear. 133.1 negative future value, then compute I per y, and it works just fine. So now we know how to find a future value, present value, and the interest rate. But what if I ask you to find the number of periods? Once again, we can simply rearrange our time value of money equation. The rearrangement goes very similarly to finding the interest rate up until the fourth step. Now what I do is take the natural log of both sides. When I take the natural log, that exponent comes down and merely multiplies by the natural log. And then I can rearrange the equation to get t in terms of the natural log of the ratio of future value to present value divided by the natural log of 1 plus r. Now, what's a natural log? You've got a button on your calculator that says ln. Now, you say, oh man, logarithms, do I really need to know that? No, of course you don't. The TI-BAII Plus can do the hard work for you. Students don't like logarithms, and neither do I. I prefer to let the TI-BAII Plus do the hard work for me. Let's do an example. If you invest $1,000 today, at some point in the future you will receive $1,402.55. Your investment earns 7%. That's 7% per year. Remember, if you're not told otherwise, you are to assume it's an annual interest rate. How many years does the investment last? Well, let's get our calculator out and find out. So here's our calculator. I'm going to first of all do second future value to clear out the time value of money keys. I'm going to put in 1402.55 as my future value, and 1000 and the plus minus key for present value. Remember the sign convention. Present value and future value must have opposite signs. 7 is our interest rate, I per y, and I'm going to compute n. I get 4.99998 and some change. In this class, I always want you to go to 2 decimal places, so we're looking at 5.00 years. Now, how do we know it's years? Because our interest rate is in per year. It has to be in years. Now, if you don't believe me, you can always go back and use the formula. If you take the natural log of 1.40255 and divide by the natural log of 1.07, you'll find out that you get 5 in return. So far, we've only looked at compounding over several periods, where we had several years with annual compounding, but sometimes compounding happens within a single period. For instance, 12% compounded monthly, 7% compounded quarterly, and 6% compounded semi-annually. Monthly compounding means compounded 12 times per year. Quarterly compounding means compounded 4 times per year. And semi-annual compounding means twice per year. All of these interest rates are stated on an annual basis, though. That 12% compounded monthly is not 12% per month. Remember, an interest rate is always assumed to be on an annual basis unless we are told otherwise. Now we're going to talk about the 2 different ways that we quote interest rates, or that we state interest rates. And it's called nominal, also known as quoted, stated, or annual percentage rate. That's the one way. It doesn't take compounding into effect. If you want to know what the interest rate is after consideration of compounding, you want to know the effective annual rate. In our examples of 12% compounded monthly, 7% compounded quarterly, and 6% compounded semi-annually, 12%, 7%, and 6% are all stated, quoted, nominal, or annual percentage rates. By the way, all those things mean the same thing. And that merely means the subperiod interest rate multiplied by the number of subperiods in the year. So for 12% compounded monthly, what would the subperiod interest rate be? Well, 12% divided by 12 periods is equal to 1%. So it's 1% per month. Now we know that when we compound that out, it's going to be greater than 12% per year. That's the effective annual rate. It takes into account the compounding within the year. So, how do we find effective annual rate? Now there are two ways that we can calculate effective annual rate. Let's use an example, 12% compounded monthly. How do we find the effective annual rate? Well, we can use the equation as given in the book, and that is open parentheses 1 plus open parentheses r over m close parentheses to the m power minus 1. Now what is m? It's the number of compoundings per period. If we're compounding monthly and the period is a year, that makes m equal to 12. So we can plug into our equation, open parentheses 1 plus open parentheses 0.12 divide by 12, close parentheses to the 12th power minus 1. And that gives us 0.1268 and some other numbers, which gives us 12.68%. Now I want you to notice that the effective annual rate is greater than the nominal rate. The nominal rate here would be 12%. This is always going to be the case as long as m is greater than 1. What would the effective annual rate be if m was 1? It would simply be 12%. So the effective annual rate will never be less than the nominal rate. Now fortunately our TI-BAII Plus also allows us to calculate these very efficiently. Let's do an example here. How we do this is to say second and then hit the 2 button. Look right above that 2 button. It says ICONV. That stands for interest rate conversion. Now nominal would be where we enter our nominal rate, which we have been given as 12. We're going to hit enter. If you don't hit enter, it's like it never even happened. Then we're going to arrow up. This is compoundings per year. On a monthly basis, that would be 12. 12, enter. If you don't hit enter, it's like it never even happened. And then I'm going to arrow up once more and hit my compute key. Notice that it has computed my effective annual rate to be 12.68% and some change. That's what we came up with earlier when we used the effective annual rate formula. So the calculator is just as good at calculating the answer and is far more efficient. Most of the interest rates that you see as a consumer, including your car loans, mortgage loans, and credit card debt, is stated as an APR, or annual percentage rate. If you want to know the true cost of the debt, you'll need to convert to the effective annual rate. Now, we know how to do that now. That was the example that we just worked. But I want to show you something here, and that is that increases in the compounding frequency increase the effective annual rate at a decreasing rate. We're going to use 12% APR as an example. If I compound that only once per year, the effective annual rate is the same as the APR, 12%. But if I compound twice per year, I get a gain of 0.36% on the effective annual rate. Now let's double that compounding to 4 times per year. Notice the effective annual rate goes up again, but not by as much as the first doubling. The first doubling got us an extra 0.36%. This second doubling only got us an extra 0.19%. And if I double again to 8 compoundings per year, I only gain 0.10%. That's what we mean by increases in the compounding frequency increase the effective annual rate at a decreasing rate. Now let's talk about continuous compounding. That's when we divide the period into an infinite number of compounding periods. So every split second we are compounding on the interest that just got earned. A simple formula for effective annual rate emerges. It's e to the r power minus 1. What is e? It's called the exponential. Mathematicians are familiar with it, the average business student not so much. Now we can do this, we can try it. We can say for 12%, e to the 0.12 minus 1 is equal to 0.12749,685, which rounds to 12.75%. Now you remember back when we did monthly compounding for a 12% nominal rate, the effective annual rate was 12.68%. So going from monthly compounding to continuous compounding did not gain us that much. We only went from 12.68% to 12.75%. Now, do the exponentials freak you out? Well, hey, let's fool the calculator into doing the work for us. I'll show you how to do that now. We go back down to iconv, and for our nominal rate, let's put in 12. Remember, you've got to hit enter. Arrow up. Now here's the trick. Put in as many 9s as the calculator will handle. I believe it's 10. And we're going to hit enter. That is as close to infinity as your calculator knows how to do. And I'm going to hit the up arrow button one more time and compute the effective annual rate. And lo and behold, it is the same number that we got before when we were doing the actually mathematical correct formula. Now why does this thing work? Well, the decreasing impact of increasing the compounding frequency. Remember, as we doubled the compounding frequency, the effective annual rate went up, but not by as much each time that we doubled. And so when you get out to 9,999,999,999 times, that's close enough to infinity that the answer comes out the same. Okay, here are a few conclusions to help you out. Always remember that $1 today is worth more than $1 tomorrow. That's the time value of money. Also remember that present value only means that it comes before future value. Present value is a cash flow occurring before a future value cash flow. Remember the TI-BAII Plus sign convention. Cash flows going in opposite directions have opposite signs. If you get error 5 or error S, that means you need to go back and fix your signs. Stated, quoted, nominal, and annual percentage rates, or APR, do not account for compounding. And by the way, those things are all the same thing. Effective annual rate, or EAR, does account for compounding. Increasing the compounding frequency increases the effective annual rate at a decreasing rate. Remember our example where we doubled the compounding frequency, but it had less and less of an effect on effective annual rate? And finally, let your calculator do the heavy lifting. If you type in as many 9s as it will take, that means the same as infinity to your TI-BAII Plus calculator for the purposes of our calculations.